Okay, hello everyone. My name is Kyson, and today I'm going to be walking through 1994 Step 2, Question 6. Okay, so we have a nice proof by induction here, involving some summation, some tan, we've got some cot, and then we've got deduce that, and we'll come to that in a second. So, obviously, base case, we need to prove true for n equals 1. So we want to show that the left-hand side is equal to the right-hand side. That's our goal. And the two facts that we're going to need to know is that cot theta is congruent to 1 over tan theta, of course, provided tan theta does not equal 0, and that tan 2 theta is congruent to 2 tan theta over 1 minus tan squared theta. Now, we can manipulate, if I just get the pen up, we can manipulate this condition here. If we let theta equal alpha over 2, this becomes tan alpha is congruent to tan alpha over 2 over 1 minus tan squared alpha over 2, right? But alpha is just some dummy variable. So really, the statement tan theta is congruent to 2 tan theta over 2 over 1 minus tan squared theta over 2 is a true statement. And we can use this to prove that the left-hand side equals the right-hand side. Okay, so let's get straight into it. Cot theta is equal to 1 over tan theta. Okay? Which means cot theta is equal to, now using this result over here, 2 tan theta over 2 over 1 minus tan squared theta over 2 to the power minus 1, because it's 1 over that. So that's 1 minus tan squared theta over 2 over 2 tan theta over 2. Okay, this is going to come in handy. So let's prove the left-hand side equals the right-hand side. So we have a half cot theta over 2 minus cot theta is equal to, well, that's just going to be 1 over 2 tan theta over 2 for this part here, minus 1 minus tan squared theta over 2 over 2 tan theta over 2. If you didn't quite get how this part was equal to a half cot theta over 2, that's simply because a half cot theta over 2 is equal to 1/2 multiplied by 1 over tan theta over 2, which equals 1 over 2 tan theta over 2. Okay? So let's be careful here. They have the same denominator, so we can subtract them. 1 minus tan squared theta over 2 okay, and let's just cancel the tan theta over 2's. So we end up with tan theta over 2 over 2, which equals 1/2 tan theta over 2. Hence, the left-hand side equals the right-hand side. Therefore, true for n equals 1, the base case. So we've proven the base case. So let's move on to our assumption. So we're going to assume for some positive integer k that the sum from k equals 1 to n of 1 over 2, oh, actually, I should make this r, oh, whoops, r equals 1 to n is equal to 1 over 2 to the n cot theta over 2 to the n minus cot theta. Now, what this statement is essentially saying is that if we have 1 over 2 tan theta over 2 plus 1 over 2 squared tan theta over 2 squared plus dot 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 plus 1 over 2 to the n tan theta over 2 to the n. That's equal to 1/2 cot theta over 2 to the n minus cot theta. Okay, that's essentially what that statement is saying there. And we're going to use that assumption to in our inductive step. So inductive step / I believe you can say inductive hypothesis. We're going to, prove that it's true. Prove true for n equals k plus 1. So we have 1/2 tan theta over 2 plus 1 over 2 squared tan theta over 2 squared plus to the k tan theta over 2 to the k plus 1 over 2 to the k plus 1 tan theta over 2 to the k plus 1. Okay, so that's going to be, by our assumption, this part is equal to 1 over 2 to the k cot theta over 2 to the k minus cot theta plus 1 over 2 to the k plus 1 tan theta over 2 to the k plus 1. Okay. Now here I'm just going to save some working. If you've done further pure 1, you should have learned about T formulae. I believe it's in further pure 1. So I'm going to let, don't worry if you haven't, you can figure this out without T formulae. This is just a quick way to do it. I'm going to let T equal tan theta over 2 to the k plus 1. So what's this going to become? Well, I'm going to have 1 over 2 to the k. This cot theta over 2 to the k is going to be multiplied by 1 minus t squared over 2t. I'm going to leave that cot theta. Now, why does this become that? Well, we know that for our T formulae, half angle formulae, we know that T equals tan theta over, wait, what am I trying to say? Oh, yes, hold on. Tan theta over 2, yeah. And we know that tan theta equals 2t over 1 minus t squared. Okay? So that means cot theta equals 1 minus t squared over 2t. There we go. Yeah, so we're going to carry on here. Now we're going to factorize out the 1 over 2 to the k plus 1. So we're going to have here 1 minus t squared over t plus t minus cot theta. That's because in this bracket here, if I do 2 to the k plus 1 and I multiply that by t, that's the same as the denominator that I had in the above line, right? And then I'm just factorizing out the 1 over 2 to the k plus 1. So here, we're just going to say t squared over t plus, it's going to be t squared over t minus cot theta. One over t minus cot theta. Cot theta, remember that t equals tan theta over 2 to the k plus 1. So this becomes 1 over 2 to the k plus 1 cot theta over 2 to the k plus 1 minus cot theta. Lovely. So we finish off with our conclusion. We've shown that the left-hand side equals the right-hand side. We've proven that it's true for n equals k plus 1. So our conclusion, we're going to say if true for n equals k, then it is shown to be true for n equals k plus 1, as it is true for n equals 1, the statement must be true for all positive integers n. Okay. Now we move on to the deduce. So we have the sum from r equals 1 to infinity of 1 over 2 to the r tan theta over 2 to the r equals 1 over theta minus cot theta. We want to show that. Okay, this is really really interesting question, but we've already proven what this sum is equal to, right? This sum is going to be equal to 1 over 2 to the n cot theta over 2 to the n. And it's actually going to be the, the limit as n tends to infinity, right, of this minus cot theta. Now, why is that true? Why is that true? Well, that sum, right, we said that that sum is equal to 1 over 2 to the n cot theta over 2 to the n. But now we need to substitute an infinity. But in terms of mathematical rigor, we should really be taking the limit as n approaches infinity. Okay? So, the limit as n approaches infinity. I'm going to just make this very clear. 1 over 2 to the n multiplied by 1 over tan theta over 2 to the n minus cot theta. Now, as n tends to infinity, let's think about what happens. What happens to theta over 2 to the n as n tends to infinity? Well, n will grow exponentially, well, not exponentially, n will grow very large, and the denominator will become very, very large, which means the overall fraction becomes very, very small. So it's going to tend to 0. Now that implies that tan theta over 2 to the n is going to tend to theta over 2 to the n. Remember, that's by the small angle approximation. Remember your small angle approximation for tan. We know that tan alpha is roughly alpha for small alpha. Okay? So that means this limit here is going to be equal to the limit as n tends to infinity of 1 over 2 to the n multiplied by 1 over, now we said that tan theta over 2 to the n is going to tend to theta over 2 to the n minus cot theta. But looky here, the 2 to the n's cancel. So we end up with 1 over theta minus cot theta. Okay. So a lovely, lovely question there. Not very long, surprisingly. And it didn't require too many tricks. Yeah, I hope you guys enjoyed this question. See you in the next one. Take care.